about O-minimal method and generalized sum product phenomenon. So thank you.
Hi everyone. First I want to thank the organizer for inviting, and thanks all of you for coming to my talk. So today I will be talking about O-minimal method and generalized sum product phenomenon. This was joint work with Yifan Jing and Suktik Roy. So these are not people from our area. So Yifan, he's in Oxford, and Suktik is now in Urbana-Champaign. And both of these people are combinatorics people. And we were working on this when one of us was at Urbana-Champaign. We'll be discussing expansion phenomenon under polynomial. So throughout A and B, we'll set them to be subset of R with the same size, and X and Y are single variable. We will let Px and Pxy and Qxy to be polynomial from with real coefficient, and we would denote PAB to be the image of element A and B in B under P, right? So for instance, if you have Pxy is just X plus Y, then PAB is just the usual subset of X of A and B. And when Qxy is XY, then QAB would just be their product set. So when we say that by large A, whenever I talk about large A, we really mean that the cardinality is large as a natural number. So if we think about it, if you take a random set A, right? Take A in random. So very likely, it is pretty unlikely that for a pair of element in a set A and B, so A and B, little a and little b, and A prime and B prime, it is pretty rare to have that the image of these under P could be the same, right? So one would expect that the size of the set of image of A under P would be roughly A squared, right? So this brings us to some natural question. When do we have the size of PAA is much smaller than A squared? And when do we have the size of PAB is much smaller than the size of A squared, which is also the same as B squared? And when do we have both PAA and QAA both much smaller than A squared? How about PAB and QAB? Oh, by the way, so if you have any question, please feel free to stop me and ask at any time. So
now P is addition and Q is multiplication?
So this is just for example.
But in the question where you ask,
we are interested in general, when is it the case that you have this is much smaller, right? So this includes for which polynomial and for which set A would have PAA much smaller than A squared.
Okay.
Right. So for instance, if when Pxy is just X plus Y, then there's an inequality called the complement inequality, which saying that size of A plus A is greater than 2 times the size of A minus 1, right? Okay, but this is an easy result. It can also be proven directly. And one may ask, okay, so when is it equal, right? So here we are looking at a situation, the smallest possible size, right? And we know that the size of A plus A is equal to 2 times the size of A minus 1, if and only if A is an arithmetic progression. And that is by a result by Gieser. But again, one can prove this directly as well. And if we relax this condition a little bit, and if we let's say A plus A is more than 17 times the size of A, then it turns out that A must be pretty closely related to an arithmetic progression. Okay, more precisely commensurable to a generalized arithmetic progression with a bounded dimension and the size that is a constant multiplied by A. But the question gets hard really, really quickly. So we do not have a structural theorem for A such that A plus A is smaller than the size of A to the power 1.1, for instance. On the other hand, we also have but we do have, so even in the simpler scale, right, addition, the question gets hard really quickly, right? But on the other hand, we do know of certain other results along this line. So for example, if Pxy is the product xy, so you have a similar conclusion, but you need to change arithmetic progression to geometric progression. And if you have something like Pxy is say x squared plus y squared, we need to change arithmetic progression to the square root of arithmetic progression. Okay, you need to be a bit careful and make sure that they are positive and things like that. But you have a result along the same line when you have for a few other polynomials. All right. So that is to say that if we really want to discuss the kind of moderate expansion problem in general, that is saying that the size of PAA is, let's say, smaller than the size of A to the power 1.1. So at the current stage of arithmetic combinatorics, nothing much we can say about the structure of the set A. So we need to give up on the structure of the set A. So because of that, we can revise the question focusing only on just the polynomial, right? So one can ask, for which polynomial xy are there arbitrarily large A such that the size of PAA is smaller than A to the power of eta, right? And it only makes sense when you're asking eta that is in the range of 1 and 2, right? Because we know that it cannot be greater than 2, right? And you can ask for which Pxy you have, so you can ask for symmetric, non-symmetric question for large A and B, which PAB is smaller than this. And you can ask similar question for pairs of polynomial. Yeah. For convenience, so let's say that if Pxy satisfying 1, we will call this an eta symmetric non-expander, which will be known by eta SNE, for symmetric non-expander, right? And if Px satisfying 2, we will say that it's just an eta non-expander. And for 3, we will get the notion of eta non-expander pair and eta symmetric non-expander pair and eta non-expander pair. Okay, so let me pause here for a second and ask if there's any question about this definition. Okay, I suppose no, so let me continue. So just for concreteness, let us ask for, let's say, eta is equal to 1.9, right? So first observation, so we already know that x plus y is a 1.9 non-symmetric non-expander pair, right? Because one can choose A to be a large arithmetic progression, and then the size of A plus A is just roughly 2 times the size of A, which is way smaller than A to the power 1.9. Yeah. And maybe with a little bit more talk, you can see that if you choose integer, then you take kx plus ly. This is also a 1.9 symmetric non-expander pair, right? So for example, if you choose k to be 1 and l to be 2, right? So you take, and you can also do A to be a large arithmetic progression, right? So if you take A, right, and you add that with 2 times of A, right? The size of that would expand by at most 3, right? Which is still way smaller than A to the power 1.9, yeah? And this, okay, with a slight modification, you can get also for rational number, right? Because you can just simply clear the denominator to showing that Qx plus Ry is a 1.9 symmetric non-expander pair. All right, it is a little bit more involved, right? Let's say when, if you are looking at polynomial look like x plus square root 2 of y, right? But it turned out that, okay, maybe x plus pi, right? So x plus pi y. So this is still a 1.9 symmetric non-expander pair. So for this, the construction of A could be a little bit more subtle. So namely, you can choose A to be this following L-dimensional arithmetic progression. So you choose K0, K1 omega plus KL omega L minus 1, where you let K is ranging from 1 to M. M is really a large number. So how many elements do we have over here? Well, you have so L place, right? And each place you have M, so you have M to the L, right? And if you are looking at the set A plus omega A, so one can check that. So you multiply everything by omega and you add everything up, right? So then the range of the thing that you add up in the range of, let's say, omega, it would be ranging from 2 to 2m minus 1, right? And you can check that the size of this is, okay, I said equal, but actually it's smaller than this number. So smaller than 2 to the L minus 1 M L plus 1, right? And notice that this 2 to the L minus 1 is just a constant, right? And M L plus 1 is not too much larger than M to the L, right? So with suitable choice of L and M, we can get that the size of PAA is smaller than A to the power 1.9 as well. Yeah. So maybe I hope I managed to convince you that with an two arbitrary real number, gamma and delta, this polynomial gamma x plus delta y, this is 1.9 symmetric non-expander. Any question? All right. But you can see that in fact x squared plus y squared is also a 1.9 symmetric expander as well, right? X squared plus y squared is not too different from x plus y, right? Instead of an arithmetic progression, you can choose A to be sort of the square root of arithmetic progression, right? And in fact, so likewise, if you choose square root 2 of x squared plus square root 3 of y squared, that is still a 1.9 symmetric non-expander, right? And let's say you take the power of this to the power of 17, nothing could change, right? Because the size of the set, it will only decrease if you take this to 17, right? Okay, so taking 17 over here doesn't mean that you take the set and you multiply together 17 times. You just look at image of this under raising to the power 17, right? So the size doesn't change, and then this is still a 1.9 symmetric non-expander. Okay, so here is perhaps a subtle point. So x plus y squared, this could be a 1.9 non-symmetric expander. And the reason is, so remember that non-symmetric expander, you are looking at the pair AB, right? So you can choose A to be an arithmetic progression and B to be a square root of arithmetic progression. Yeah, so putting together, you see that it does not expand too much. Yeah. On the other hand, x plus y squared should not be a 1.9 symmetric non-expander. And the reason is, let's say you choose A to be an arithmetic progression, right? So A squared, it could be a sequence of square arithmetic progression. And if you take this and then you add to an arithmetic progression, thing could just blow up, right? You could generally not be expect that you will get something small, right? And so heuristically, this should not be a 1.9 symmetric non-expander. Yep. Even though we don't have a proof, by the way. So, okay, but let's get to that a bit later. So in general, you would expect that if you are taking like gamma of ux plus delta uy, where x, the u is the same, right? So let's say x squared, u can be x squared over here, and then you apply to function of this. This could be a 1.9 symmetric non-expander. And if you are taking f of ux vy, this could be a 1.9 non-expander, right? But not a 1.9 symmetric expander unless v is a constant multiple of u. Okay, so over here we have f, u, and v are univariate polynomials. All right, so on the multiplicative side, you can see that actually f of u to the mx, u to the ny, this could be a 1.9 symmetric non-expander. So there's this conjecture that sort of like the folkloric conjecture, which is saying that if you are looking at a polynomial x, y, it is a 1.9 symmetric non-expander if and only if it has this form or this form. Yeah. And the polynomial pxy is a 1.9 non-symmetric expander if and only if it has the form f of ux plus vy or f ux times vy.
Min?
Right.
So,
Yes.
so now, is there anything special with 1.9, or it just means something smaller than 2, or?
Yeah, it's a 1.9, just a number that is smaller than 2. Yes.
Okay, so now in the conjecture, it's just, okay, any number.
Right, right. So this is a folkloric conjecture, but and this conjecture is very likely true, but it is really hard, right? So it is probably as hard as the autosimilarity sum product conjecture. And well, it's pretty safe to saying that an answer to this conjecture would be a revolutionary result in additive combinatorics and probably also harmonic analysis. And one thing that I want to note is that, so for this conjecture, if you are varying the exponent, the larger the exponent is, the harder the problem is, right? Because the larger the exponent is, means you are weakening the non-expanding condition, right? And as a consequence, the theorem is getting stronger when it's harder to prove a result for 1.9 compared to a result by 1.1. Yeah.
So, Min, there's a question from the people online. Are U and V necessarily of the same degree?
No, U and V need not be the same degree. So, for example, x plus y squared, that would still be a non-symmetric expander, right? But it's just that it's not a symmetric it could be a non-expander, but it is just not a symmetric non-expander. All right, is that clear? Oh, by the way, may I ask how many more minutes do I have? Is it 10 or is it just 5?
Let's see.
10.
Oh, yeah.
10. Okay, thanks. So with that, so thanks for
Even more than 10, 13.
Yeah. So let me say our first main result. So our first main result is that so it is a result to work this conjecture, but with weaker exponential bound. So the polynomial pxy is 1.25 symmetric non-expander, even only if it has this form or this form. So the expected form, but only with the weaker bound of 1.25 instead of like 1.9. Yeah. And this is the current best record of this type of result. And okay, in fact, maybe the only kind of result of this type that is known right now. In the case of the non-expander that is non-symmetric, the records is held by the result by Alekes and Royal, which saying that this polynomial is 1.33 non-symmetric expander, even only if it has the expected form with univariate at U and V. All right, so you might wonder what are these two numbers? 1.25 is 5/4, and 1.33 is just 4/3, right? And okay, I didn't write it. Should be more 3, but I didn't write them. And maybe in model theory, you probably could hear the name Alekes more often than Alekes-Ronjai, but essentially they're the same result, which and you can think of Alekes as sort of like the implicit function theorem version of Alekes-Ronjai, but more or less they're the same. Okay, so over here we only state the result for the real number, but we also have the same result for complex number. And just by model theoretic transfer, we can get the same result for all the fields with characteristic 0. And you can also get transfer to get a result for characteristic P for large P. Okay, so maybe when I'm saying that the current record holder is 1.33, so there is a chance that this can be improved into 4.3 plus 1/1000 using some higher Fourier analysis along the line of work by George Chaikin. but I don't think that anybody tried yet. Okay, but I'm not 100% sure about that. But there's a chance that the current technique is you have to improve it to 4.3 plus 1/1000. All right, and so you might think that our result would immediately be implied by Elekes-Ronjai, right? But it's not the case, right? So Elekes-Ronjai only implies that you have the f, ux, and by over here, but it doesn't say, for instance, that these two polynomials has the same degree, right? But in our result, it must have same degree, right? So, and in particular, one needs to be a constant multiple of one another, right? And in some way, this Karp conclusion is the correct Karp conclusion that one should expect. All right, so one thing that is a bit surprising is that in order for us to prove this symmetric result, so now that we need to prove result for two polynomials. So you want to show that if px and qxy it form 1.25 non-expanding pair, if and only if it's either of the additive form or either of the multiplicative form, right? And somehow, if you're looking at this, right? So if you're looking at inside the polynomial f over here and inside the polynomial g over here, sorry, there's a typo over here. This should be delta. Okay, this is gamma 2 and this is delta 2, right? So the inner part of this needs to look reasonably similar to the inner part of this. Okay, with f, g, u, v, okay, only please satisfy the obvious condition, right? This result, so for example, in particular, it implies that if you are take the polynomial x plus y and x times y, right? Well, they do not, so one of them is addition and one of them is multiplication. So they cannot form a non-symmetric expanding pair, right? And as a consequence, you can see that you can recover the sum product phenomenon from this result. So that's why this two polynomial result, it can be considered as a generalized sum product result. All right. So from the proof from this theorem for two polynomial, you can prove the earlier stated result using a trick. Okay, so suppose you have pxy is a 1.25 symmetric non-expanding pair. We would define p tilde to be p tilde xy to be p of yx. We flip the variable, and then you're applying the above. So now you will have pxy is non-symmetric expanding pair in particular, and p tilde xy is also a non-symmetric expanding pair with the set A, right? With the set the pair AA. So as a consequence, you can use above result, and you get that the structure of pxy must be really the same as pyx, right? And that basically forces that over here you need to have the same polynomial, and that is basically the idea. So probably I wouldn't have that much time.
Min,
yes.
There's another question.
Yes.
Are the if and only if either mutually exclusive? Maybe you can look at the question.
Yeah, so if and only if, yes, this can be proven to be mutually exclusive. Right, yes, they are mutually exclusive, right? Can be proven. Yeah. All right, so maybe since I only have perhaps 1 minute left, so let me tell you perhaps how, instead of going into the proof, let me tell you a little bit about how this fit into the framework of model theory.
You have 5 more minutes, so.
Oh, I have 5 more minutes. Oh,
yes, I think you're okay.
Thanks. Okay, so maybe then I can say a few words about the proof then. So how do we're trying to prove, look at this proof. So we're looking at the pair pxy and qxy, which form 1.25 non-symmetric, non-expanding pair, right? So in particular, each of these polynomials need to be a 1.25 non-expanding, right? So we know that pxy you apply Elegans-Ranyel to get that Pxy has the form f of u1x plus v1y or f of u1x v1y, right? And we also can apply Elegans-Ranyel independently, individually to Qxy. You get it has the form g u2x plus v2y or g of u2x v2y, right? So the point is that you want to rule out, at first you want to rule out the case that P, it has the additive form, and Q, it has the multiplicative form, right? And in the situation that both P and Q both has the same additive form, you want to show that U1 is really similar to U2 and V1 is really similar to V2, right? So I would mention, so for instance, right? So for the first one, how to rule out, let's say, x plus y and x times y. So for that, we basically you can follow the proof of the sum product with exponent 1.25, which use Symmetry-Trotter theorem. And you can, using that proof, you can rule out this case. So in general, to handle the other case, you also use a similar strategy, but you need to replace Symmetry-Trotter by the generalization of Symmetry-Trotter by Fox, Bass, Xavier, okay, the five people paper. And plus one technique from Modularity, but in this case, actually, semi-algebraic is enough. But the nature of the technique that we use is kind of rare Modularity. Yeah. And okay, so let me tell you how this fit into a model theoretic point of view, right? So in a very big way, our theorem you can be interpreted as saying that if Pxy you want it to be 1.25 as a symmetric non-expanding pair, Pxy must be something like just addition or multiplication. So in some way there must be really modular in a certain way. Except I'm not totally sure how to make precise of modularity here, perhaps using some pseudo dimension, but I don't know. But okay, as long as you can accept that this is about modularity, you can see this result in the framework of this recent result of exploring consequence of modularity in combinatorics. So in general, when we expect some statement along the line that if you have non-modularity, you would have some product type phenomenon and certain cap density take non-integer value. And if you have modularity, you have certain cap density take integer value, right? So the result in the first slide was obtained by a lot of people, and the result in the second slide was obtained by some other people. Okay, so finally, maybe let me just mention one or two open questions. So which we thought that we would do it at some point, but we never managed to come around to do it. So first of all, we really believe that somehow we should be able to use Symmetry-Trotter in a more clever way to improve our result from 1.25 to 1.33. So improve our record, right? And we think that there should be some kind of similar result when instead of polynomial, you replace it by continuous definable function in R or QP, or even in zero finite field of characteristic P, right? But here you need to do the correct topology, which is, well, the eta open topology. So recently, Artem, Kobe, and Sergey has a result along the line of Elegans Sabor, but their result is not very explicit. So it would be nice to get an explicit result for Rx, right? And then after that, we can also use our machinery, and this could truly be a minimal instead of just semi-algebraic. All right, and that's all I have to say for today. Thanks very much.
Are there any questions? People here from the Zoom audience? Then I have a question. What's so special about 1.25? I mean,
yes.
What did you use it? I mean,
oh, 1.25, just 5 over 4.
Yeah, of course. But in the, in the outline of the proof, I mean.
Yeah. Yeah, of course. Yeah, of course. Sorry. So the 1.25 that came out from the fact that we are using semi-trotter theorem, right? So there is a bound in semi-trotter theorem, and that bound, if you are applying it, you would get the bound 1.25 in this result. So I think that there's a more clever way to apply it to get 1.33, but we don't know how to do it in this more clever way, at least over here. But I'm sure other people need to know how to do it. Yeah, I hope that answered the question without going too much into the proof.
Okay, thank you. Any more questions?
Hi, Minh. I have a similar question. Can you hear me? Yeah. So it's the bound
yes.
from semi-trotter theorem. So do we know if the bound for semi-trotter in the semi-algebraic case is the best already? I mean, I think
the bound in semi-trotter is sharp. Yeah, so the bound in semi-trotter is sharp, so you cannot improve the bound in semi-trotter. So if we want to really improve this result beyond 4/3, one need a very different technique somehow.
Yeah, okay, yeah, I was thinking of this. So if you, yeah, okay. Yeah, thanks.
Any more questions? Okay, so let's thank Minh again. So just a reminder, announcement regarding tomorrow. Tomorrow is an unusual day, and we'll start at 10:25 in the morning. 25 Toronto time, of course. 10:25, yes. The day itself?
So it'll be like a half-hour talk, 10:25 to that plus 30 minutes.
55?
55, 10:55, and then at 11 we'll have an hour. Yes?
50 minutes.
Yeah, 50-minute talk by Gabe. Yeah.